Our next speaker is Sung. He is a Lisper, like many of us. He's interested in correctness, especially of concurrent programs. That's why he came to Clojure, which is, in my opinion, a very good idea. And he will talk about automated correctness analysis for core.async. Please give him a warm welcoming applause.
Okay, so guten Morgen. Wie geht's? Good? Nicht good? Okay, well, thank you. So it's been, I was counting the years, and it's like half a lifetime of my lifetime ago since I had a little bit of German in high school, so I think it's in the interest of all of us if I continue just in English, all right? So let's do that. I was looking at the program, and then I realized that probably my background is a bit different from most of the speakers here today, so I thought I'd summarize it in 2 bullet points. So let's have a look. First of all, I don't work for a company, and I also don't work with customers. So this sort of makes me a hobbyist, I suppose. But if I'm a hobbyist, then at least I'm a very lucky one, because I do get paid to play with Clojure. All right? So how does that work? Well, you need to work in a university. Right? So I'm assistant professor in the Open University of the Netherlands. I'm also a researcher in Centrum Wiskunde en Informatica, which is the Dutch National Research Institute for Computer Science. And yeah, so these 2 bullet points are true, but I think my employer would appreciate it if I would stop saying that I play, right? So I do research. But I mean, at the end of the day, there's not a huge difference, I suppose. So, okay, I want to talk today about core.async, but I'm not sure if all of you have used it or seen it before, so let me summarize it very briefly. So here's a screenshot of the blog post that Rich Hickey wrote like 9 years ago to introduce the library. And I want to highlight just a few of the statements that he makes in this blog post. So first of all, he says that, let me move this pointer away, that one of the objectives of core.async is to build upon the work done on CSP. Now, CSP, it stands for Communicating Sequential Processes, and it's essentially a kind of a theoretical model of concurrency. Okay, so that sounds kind of complicated, and it actually is kind of complicated, but I don't want to, bore all of you guys with that today here. So the only thing you need to know about CSP in the context of core.async is that when you perceive your concurrent programs through this CSP kind of looking glass, you have processes, and you have channels between processes, and that's it. That's all you need to know, right? So the idea is these processes, they perform some local computations, and then at some point, they need to share data with each other, right? So they perform send and receive operations on the channels, and yeah, that's essentially the kind of programming model that core.async offers also to Clojure programmers, right? So you have functions to spawn threads, to create channels, to perform send and receive operations for messages, and that's, well, that's in a very tiny nutshell what core.async is about. So in this blog post, Rich explains very nicely, the rationale behind core.async and a little bit of the usage as well. And then towards the end of this blog post, he says, well, CSP proper is amenable to automated correctness analysis, but no work has been done on that front for core.async as yet. Okay? So this was in 2013. Now, fast forward 5 years later, student comes to me, and he says, well, I want to do my final thesis project somehow in the intersection of Clojure and your research area. And my research area, it happens to be include automated correctness analysis for concurrent programs. So this was sort of a very good match. And then we looked around a bit to see if in the 5 years that had passed, anyone else had started to work on this, but we couldn't find anything. And so this student, he started to work on this. And actually, we wrote a few scientific papers about this as well. But it wouldn't be the first time, I guess, that people in universities, they invent all kinds of things, and they think it's very nice, and most of the time it is, but it's totally unuseful in practice, right? Especially in computer science, this, we're very good at this. And so I guess well, the aim of my talk today, first of all, is to sort of entertain you guys, right? So I just want to show you something that I think is really cool, and I hope that you find it cool as well. But also, we're very much looking forward to hearing your opinions on the things that we do. So if you think it's useful, that's good for us to hear. If you think it's totally useless, it's even better for us to hear, because it can sort of help us shape our research agendas, right? So I'm very much looking forward to talking to you guys in the coffee breaks and during dinner and so on. All right, so my plan for this presentation is, well, it consists of 3 parts, I would say. So first, I'll do a very tiny crash course on core.async, so we're all on the same page. And then I will explain you what kind of mistakes are easy to make when you use this library. And then finally, I'll show you a little bit of the techniques that we developed to do this kind of automated correctness analysis, okay? So let's start with the crash course, all right? And I want to do that based on another blog post from 2013 written by Alex Miller, who introduces the main concepts of core.async in a very appealing example, at least to me, namely rock, paper, scissors. And we're going to assume for simplicity that anyone here has played rock, paper, scissors at least once in his or her life, okay? So what we're going to do is, so we have here sort of a high-level picture of what the application looks like. So we'll have 4 processes, Alice, Bob, Judge, and main. And the players are Alice and Bob, okay? So the idea is that Alice and Bob, they're both picking their own move, rock, paper, or scissors. And then they're sending information about this move through this channel of theirs to the judge. Okay? And then the judge is going to decide who is the winner and send the name of the winner to the main thread, and the main thread is going to print it to the command line. That's what we're going to do. And I'm going to use the terms thread and process interchangeably, by the way, during the presentation. Purists will say that there's a difference, and there is, but it's not really relevant for my talk, so please bear with me on that one. Okay, so this is the general idea. Let me just show you the code, all right? Code. So first thing that Alex does in the blog post is he just defines some general domain concepts for rock, paper, scissors, which is kind of simple. So we have moves, rock, paper, and scissors. And we have a map that defines which move beats which other move, right? So for instance, rock beats scissors, okay? And then we also have a function that takes 2 arguments, 2 pairs essentially, namely consisting of the name of the player and the move that the player has played. And then this function, it computes which is the winner, right? Doesn't matter so much. I mean, you can look at it, but the details don't matter here. And then we also have a simple report function to print who is the winner, all right? So this is all, let's say, the raw computations that we need to do for rock, paper, scissors, all right? So what I'm going to do now is I'm going to load this core.async library, right? Because we need it to actually define the threads and the channels that we're going to use in this program. And I'll do that using 2 functions, okay? So the first function that I'll write is one to spawn the players and the channels that the players are using. So let's have a look at that. It's called randPlayer because the players are going to pick their moves randomly. And the general structure looks as follows, right? So first thing we do is we create a channel, right? Then we spawn a thread. And spawning a thread, of course, means that the body of the thread is going to be executed asynchronously, independently of, well, let's say the main thread, right? So after spawning this thread, immediately, you can also return a reference to the channel that you just created. And this is very useful because it means that, inside the body of the thread, right, you can send a value, send a message through the thing, and then still the main thread has a reference to the channel, so it can also receive it, right? So you can do that in another thread. That's very useful. Okay, so let's also try to fill the body. Well, rock, paper, scissors, really simple. So we need to do only one thing, right? Which is send a message. And this greater than bang bang function, that's the send operation in core.async. So we send a message through this new channel, and the thing we're sending is a pair consisting of the name of the player and a random move that the player has selected. Okay, fair enough. We'll call this function twice, but I'll show it on one of the next slides. We'll also need a function for the judge, and the general anatomy of this function is the same, right? So again, we create here this channel, we spawn a thread, we return a reference to this new channel directly in the main thread. It's just that the body is a little bit more complicated, right? So as you saw on the previous slide, what we want to happen is that the judge receives these messages from the 2 players. And so actually, this judge needs to have access to these channels as well, right? So what we'll do is we'll have these 2 arguments of the function, P1 and P2, and they're supposed to be references to the channels that we just created for the players as well. Okay? So then the judge, he receives these messages through these channels, and then, well, he can compute the winner and send the name of this winner on its own output channel. Okay? So yeah, this is basically all we need. Rock, paper, scissors on one slide. Of course, we also need a bit of glue code to wire everything together, and that's what I'll show you here. right? So what happens is that we start with the main thread. That's fine. Then what the main thread does, it calls this rand player function for Alice. And so what happens is that this new thread is spawned, including this new channel. But this new channel at this point is still a bit dangling, right? Because we know that Alice is going to perform the send operation, but we haven't created the judge yet who is going to do the receive. So at this point, the channel is still dangling. And the same holds for Bob, okay? Now, once the main thread also calls this judge function, this is basically the point at which we sort of connect the dangling channels to the judge, and then, well, finally also, because the main thread will call the receive function on the channel of the judge, we get the whole program, right? And yeah, this is basically it. So we can now go to IntelliJ, I suppose. Is this readable? Sort of. So let's just have a look at that it actually executes, right? So this is just the namespace for all these generic rock, paper, scissors concepts. Here we have I'm not seeing my pointer on my screen. Right. So here we have the function for the player. It's exactly the same as on the slide. We have also the function for the judge, exactly the same as on the slide. And here we have this glue code, right, that wires everything together. I will move it a bit up, right, so you can see. It's just that I also I wrapped it in a test so we can easily execute it here. And then we'll see what happens. Takes a bit of time. Maybe I should make this a bit bigger so also people in the back can see it. Can read it. And the output that we get is no one wins. Yeah, that happens a lot with rock, paper, scissors, right? So tough luck here. But if we would run it again, then perhaps we would have a player that wins. OK, back to the slides. So what kind of problems can you encounter when you use core async in this way? So what kind of programming mistakes can you make? And I think there are two sort of categories of mistakes. The first category is the kind of mistakes that you get when you get the wiring wrong. Right? So here in this case, I mean, the main thread is supposed to read or receive from Z, right? But here, I made a mistake, right? I let it read from Y. And it essentially means now that this channel, which used to be from Bob to Judge, is now shared also with the main thread. And so the main thread and Judge, they are actually sort of competing for access to this channel. And this may remind you a little bit like classical data races, right? Where processes, they're sort of competing to get access to shared data. It's similar here, except it's not shared data, but it's a shared channel. And so you can already feel, perhaps, that this can lead to trouble. And it does, right? So regardless of who wins the race, main or judge, we will, in both cases, get erroneous behavior. And I can show you what happens. Oh, this is the wrong, yeah, here. So let's see. Here we have the other version, the faulty version of the wiring, right? I'm reading here from Y. And so when I run this, let's see what happens. So if I would use the life hack, I would now, of course, try to predict what's going to happen, but I already know because I prepared this. So anyway, so what we get is Bob : rock wins. Okay, and this is, well, not really the format that we expected to get from the output, because what's happening here is that main wins the race. So the main thread receives the message that Bob actually meant to send to the judge. And so the main thread, it just prints it as if this is the name of the winner of the game, but obviously it isn't, right? So the kind of error that we have here is that the output is wrong, but at least we can sort of simply recognize it because the type or the format of the output does not comply with what we expected to receive, right? So at least that's something. So this is the error that we get when main wins. But of course, we can also have the situation where the judge wins the race. And so here I have another test. And well, to show you, I mean, I'm sort of forcing the judge now to win by having this extra sleep instruction to delay the main thread a little bit. And so I'm running this test, and it's running and running and running. And obviously, these 500 milliseconds have passed now, right? So something else is going wrong here. And the thing that's going wrong here is that we got stuck in a deadlock, okay? So the deadlock that we get here, just to explain it based on this picture, is that well, judge wins the race, right? So we receive the message from Bob, but main is also still waiting to receive something from Bob, right? But Bob is going to send only one message, right? So yeah, main is basically stuck forever, waiting for something that will never happen. And so yeah, we do have a deadlock here. And so for this first category of let's say programming mistakes where we get the wiring wrong, at least two kinds of problems we can get, namely deadlock or wrong output, where the wrong output has the wrong type. That's at least the example that we saw in this presentation so far. Okay, that's one thing. But there is more, right? More can go wrong. Even if we get the wiring right, of course, we can still make mistakes in the way in which the processes actually use the channels that are given. So here I have another version of the judge, and the mistake that I made here is that essentially I turned it into an unfair version. So he receives only from the first player, then extracts the name of the message, and then simply says, okay, this player was the winner, right? So Bob is basically, he's completely disregarded. And so when we run this, let's see, this is the final test that I can show you. So what do we do here? Well, we're redefining the judge, of course. Maybe I can pull it a little bit down. So we're redefining the judge to actually have this faulty behavior. And then when we run the test, we get Alice wins. Alice wins, right? Now, the problem with this is that this is actually the expected output, right? Or at least the format. So if we just read this, then it's not obvious to us that something has went wrong, even though we know for sure that there was a mistake here. So that's really kind of bad. You get output, but you don't know. You cannot trust the output in some sense. Okay, so that's the second kind of problems that you can get, right? You can get the wrong output and where the formatting or the type is okay, but the value really is not. And so what's interesting, I think, if you look at all these faulty executions, is that the underlying problem somehow seems to be that the processes or the threads, they don't comply with the intended communication protocol that I had in mind when I started to write this application, right? So the intended communication protocol was that you have first Alice to judge, then Bob to judge, and then judge to main, right? That's what I wanted to do. But in each of these faulty executions, something goes wrong in terms of this protocol, right? And so when I talk about automated correctness analysis for core.async, really what I'm doing is I'm checking compliance. I want to check that every execution of my concurrent program satisfies this intended communication protocol that I have in mind. And the principle that we're having here is fail early, fail loudly. So as soon as we detect a violation, we immediately want to throw an exception to indicate to the programmer that something is wrong. Okay? Okay, so on the rest of this slide, I just want to show you at a high level the techniques that we use to do this form of automated correctness analysis. And then on the next slide, I'll show you how you can sort of deploy this inside existing core.async code. Okay, so let's see, what kind of ingredients do we need? Well, first of all, we need to have a program, right? So let's just assume that we have a program. That's fine. Then the first real ingredient that we need is what is called instrumentation. And this is just a fancy word to say that we build a thin wrapper around the program that allows us to sort of register or log events of interest. And the events of interest in our case are sends and receives through channels. Okay? So with this instrumentation, at least we can get a sort of a log of the things that happen. But this is not enough, right? Because we also want to check that the logs sort of comply with this intended communication protocol. And so we need to have a second component, which is a monitor, right? And at runtime, what happens is that this instrumentation, it will detect or log these events of interest, and it will then immediately ask the monitor if this is okay relative to this intended protocol. And if it is, then the monitor will inform the instrumentation accordingly, and everything will be fine. And if it's not, then something else needs to happen. Okay, so that is sort of the basic operations. But I guess the key question at this point is, how does this monitor know, what is this intended communication protocol, right? It cannot just probe the mind of the programmer. So we need to be more explicit about this, and this is the final ingredient, right? It's a specification, right? So we need to tell the monitor what it is supposed to look at. And so for this specification, we have a kind of a specification language. It's like an embedded DSL, very much inspired by regular expressions in spec alpha. Okay, so in spec alpha, you have regular expressions to specify, patterns of sequences of data, right? And here we have essentially the same, except we don't have sequences of data, but sequences of communications, right? So we're using somehow the same notation. So cat here stands for concatenation. So we just want to do all these things. And then this arrow macro is just a communication, right? So we're specifying here first the communication from Alice to judge, then from Bob to judge, and then from judge to main, exactly as the thing that we intended as well. And so when we start to execute this, then the following happens, right? So at some point, there's this communication from Alice to judge, okay? And the instrumentation will ask the monitor, whether this message is okay, right? And so the monitor will then check the specification and see that indeed the first communication that's supposed to happen is from Alice to judge. And so it will say, yes, this is okay. Okay, so the instrumentation is fine, everybody is happy. Some point later, Bob does this communication with Judge. And so again, the instrumentation asks if this is OK. The monitor checks the specification, and it has also marked that this first communication has now happened. So it doesn't need to look at that anymore. So again, it says, yes, OK, this is fine. So the program continues, and then finally we also have this from main to Judge, and this is also OK. So at the end of the day, you get the assurance that when the program terminates, the communications that you have seen, that you've observed, that they do comply with this protocol, which is nice. But now we also had these, erroneous programs, and so here let's have a look what happens then. So we start again with this communication from Alice to Judge, which is fine. We already saw this. But now there's a choice, right? Two things can happen. Either main wins the race or Judge wins the race and receives from Bob. So if main wins the race and receives from Bob, the instrumentation asks the monitor, is this message from Bob to main, is this allowed to happen? But now the specification says, no, you cannot do this, right? Because Bob is supposed to send to Judge. And so the monitor will now say, no, you cannot do that. And then the instrumentation will act upon this and say, OK, well, if this is not allowed, then we need to throw an exception because we need to fail early, fail loudly. OK? So then you get an exception, and then you get this feedback that something is wrong. So this is one option. The other option is that Judge wins the race. So if we backtrack a little, then we go back to this situation. And now we get this communication from Bob to Judge. And this is actually in compliance with this protocol. So we say yes. So the instrumentation is happy, and it will continue to execute the program. But we have already seen that in this case, we actually get a deadlock, right? And so fortunately, the instrumentation is also capable of picking up this. Okay, so this kind of deadlock, it's also because the operations happen on the wrong channel, so to speak. So this is a kind of a protocol violation as well. And so the instrumentation picks it up and also throws an exception in this case. Final example we had was when the judge was faulty. Yeah, basically it's the same, right? So the first communication is OK, but the second one from Judge to main, this is not OK. And so again, here we have an exception. Okay, so this is sort of, at a high level, how this automated correctness analysis works. So as a programmer, the only thing you need to do really is define this specification. OK, so how can you deploy this in existing core async programs? So here again, we have rock, paper, scissors that we have already seen before. The only thing that I need to change, well, first of all, is I need to load our own library instead of the original core async library. The reason that is, so this is basically the instrumentation, right, the wrapper. So we wrap around a number of functions in the original core async library. So the signatures are exactly the same. And then you add this instrumentation. And to configure the instrumentation properly, we also need to know for each of the channels which are the intended sender, the intended receiver. And also, well, we have this M here, which is the monitor that we're using to monitor this channel, of course. And so we also need to define the monitor. And the monitor, well, we also have a function for that. So we define this specification. And well, we would have loved to call this function def protocol, but it's already something else, so we cannot use that. So we have def session, right, a communication session, if you will. And then we have this function to define the monitor. And well, in this way, you can add this. So let's have a look at this as well. So I have another namespace here, where here I have the protocol, right? Here I construct a monitor. Here I have this extra configuration data for the channels. And now I can run my tests again. So these are essentially the same ones as before. Maybe I can move it down a little bit. Yes. So okay, here we do not get an exception. This time Alice wins. Okay, so that can happen. Now we have this version where we didn't get the wiring right. And so here, now at this point, we get an exception. And the details of the message don't matter so much, right? It just gives you some additional debugging information that sort of tries to clarify why you're seeing this exception and what is the reason that the actual behavior does not comply with the expected one. And so this is the situation where the main thread won the race. So we also had this version where the judge wins the race. And we get another exception, but here, the message is a bit different. Here it says, oh, you run into a deadlock. Okay, so, and then finally, the last example that we had was with this faulty judge. Yeah, hopefully we get an exception here too. Yeah, so this all kind of seems to work. Okay, so let me end with a short pitch, sort of the things that we can and cannot do. So currently we support only a fragment of core.async because it's really an extensive library, right? So we're focusing only on the core features right now. So we have threads, we have channels, both unbuffered and buffered ones, right? So I've shown you only the buffered ones in this presentation so far, but we also have only the unbuffered ones, but we have the buffered ones as well. We have timeouts, and then we have the main operations: send, receive, alt, and close. Then the kind of checks that we do it's for deadlocks and for non-compliance, right, as I've shown you. The checks for deadlocks, they are sound but not complete, which means that if you get an exception, then you can be sure that there really was a deadlock, but we're missing some deadlocks as well, right? So in that sense, we're not complete. And it's also a little bit of an experimental feature yet because, well, checking deadlocks is actually kind of hard, so we need to do some more research on this as well. For non-compliance, we have soundness and completeness, which means that if you get an exception, there really was incompliant behavior, and if there's incompliant behavior, you are bound to get an exception. So the guarantees that we offer there are much stronger than for deadlocks. And regarding the ergonomics, so we have this embedded DSL for these specifications, which is inspired by spec alpha. And what I didn't show, but what we also have, is checks for data, right? So very often you also want to say something about, the contents of the messages that are being sent, and we can have we can do those kinds of checks as well. And I think, well, the amount of changes that you need to make to your code to actually deploy this is kind of well, it's not so much, right? So we try to be lightweight in this sense. Okay, then there's one more topic that perhaps a question that I might anticipate, and that's about performance, right? Because we're doing all these extra analysis at runtime, so we are bound to be slower than without this. Now, I prepared a few slides for this as well, so we did some benchmarks, but I think I'm going to skip over them because I'm running out of time. So the conclusion is it's not too bad, but it's not great either. Okay, so in the benchmarks that we did, in some cases the overhead we get is less than 5%, which is kind of okay, I guess. I mean, you could run this in production environments as well. But in other cases, the slowdowns we're observing is like 3 to 5 times. So I wouldn't run that in production. But still, I think it could be useful, in development, right, as a debugging tool or as a testing tool, kind of similar to memory profilers, right? When you run a memory profiler, you're also maybe 10 times slower, but it's still very useful to catch bugs. Okay, so this is all I wanted to say. This is the project page. The QR code leads you there. It contains more documentation. Most of the documentation actually exists right now as these scientific papers, but I think they're kind of accessible to read, so that should be possible. I really want to mention the other contributors to the project, which are Ruben Hamers and Erik Horlings. And Ruben was actually the student that started this in 2018, so without him, I really wouldn't have been here. There's a bunch of future work that we want to do. I'm not going to mention all of it, but I do want to mention the last point, move towards production readiness, because I think the current state of this library, well, I did the live demo, it all seems to work, but I would say it's still, proof of concept or prototype-y kind of experimental stuff. And so if you would like to use this actually, or if you're a company and you want to use this, then just reach out to us and then we can sort of discuss what we would need to do to sort of professionalize what we have right now to make it actually useful for people in the real world, so to speak. All right, that's all I wanted to say. Thank you very much for listening. I really enjoyed being here.